Hey friend, welcome. If you're here to unwind, to quiet your mind, or drift off while learning something fascinating, you're in the right place. Tonight, we're exploring the mysteries of gravity, gently, slowly, one idea at a time. So settle in, let your thoughts soften, and let's begin. Chapter 1. What is gravity? The most familiar unknown. Gravity is one of the first physical realities we ever meet. As an infant, you feel it in the weight of your own body, in the way toys always fall toward the floor and never drift toward the ceiling. It holds your feet to the ground, guides the water that runs from the tap, and shapes the arc of anything you throw. Yet, in modern physics, gravity is also one of the deepest mysteries, a phenomenon that we can describe with remarkable precision, while still not fully understanding what it truly is. For a long time, people thought of falling as a kind of natural tendency, different from the motion of the moon or the wandering of planets in the night sky. The breakthrough came when Isaac Newton realized that the gentle pull that makes an apple fall and the majestic motion that keeps the moon in orbit are not two different things, but the same universal interaction. He expressed this as a law that says every piece of matter attracts every other piece of matter, with a force that depends on how massive the objects are and how far apart they are. This law of universal gravitation was revolutionary because it unified heaven and earth. The same relation can describe a stone dropped from a tower, an artificial satellite circling the planet, or the orbit of a distant moon around a giant planet. It told physicists that the universe is orderly and that the same rules apply everywhere, not just in special places. Observations of planetary motion, the paths of comets, and the behavior of projectiles all fell into place under this picture. In the Newtonian picture, gravity behaves like a force that acts at a distance. The Earth pulls on you even though there is empty space between your body and the center of the planet. There is no intermediate physical connection in this description. Only the mathematical statement that a force exists. For everyday purposes, this view works extremely well. Engineers use it to calculate satellite orbits, space agencies use it to plan missions, and it explains why the planets follow paths that match what astronomers observe. The strength of the gravitational pull in this framework depends only on mass and distance, and it is always attractive. Yet there were small cracks in this picture. When astronomers tracked the orbit of the planet Mercury with high precision, they found a tiny mismatch between the observed path and what Newtonian gravity predicted. That mismatch remained unexplained for decades. Meanwhile, physicists were gently pushing the boundaries of mechanics and light, and a new idea about space and time themselves was slowly forming in the mind of Albert Einstein. Einstein's general theory of relativity offered a different way to think about gravity. Instead of treating gravity as a mysterious force reaching across space, it describes gravity as the curvature of space-time itself. Matter and energy tell space-time how to curve, and that curved space-time tells matter and light how to move. In this view, the Earth does not pull the moon along a curved path. Rather, the Earth creates a dent in the fabric of space-time, and the moon simply follows the straightest possible path within that curved geometry. A common analogy is to imagine a stretched rubber sheet representing space-time. When you place a heavy ball onto the sheet, it sinks, creating a curved depression. A smaller ball rolling nearby will appear to be pulled toward the heavy one, but in reality, it is just following the curved surface. In actual physics, space-time is not a two-dimensional sheet, but a four-dimensional structure, with 3 dimensions of space and 1 of time. Yet the analogy helps to convey the core idea. Gravity is geometry. General relativity was not just a philosophical reinterpretation. It made testable predictions. It explained the strange behavior of Mercury's orbit that Newtonian gravity could not. It predicted that light passing near a massive object would bend, not because light has mass, but because space-time itself is curved. This was confirmed when starlight passing near the sun during a total solar eclipse was observed to shift by roughly the amount Einstein's equations predicted. It also predicted that time runs more slowly in stronger gravitational fields, so clocks on the surface of Earth tick a little bit more slowly than clocks high above. These effects are not just theoretical curiosities. The global positioning system relies on satellites that orbit high above Earth's surface. The clocks on those satellites experience both weaker gravity and a different state of motion than clocks on the ground. Without correcting for the small differences predicted by general relativity, the positioning system would accumulate errors that would quickly render it useless for navigation. The fact that satellites work as expected is a quiet, daily confirmation that gravity really is connected to the geometry of space-time. Despite all this progress, gravity remains in many ways the most familiar unknown. On the one hand, we can calculate the motion of planets, the structure of galaxies, and the paths of spacecraft using our 2 main pictures: the Newtonian force law for many practical problems, and the relativistic curvature of space-time for situations where speeds are high or fields are strong. On the other hand, we still do not know how to reconcile gravity with quantum mechanics, the framework that governs the behavior of particles on the smallest scales. All the other fundamental interactions of nature are described within a single quantum field theory, often summarized as the standard model of particle physics. Gravity remains outside this framework. Attempts to quantize it, to describe space-time itself as made of discrete quanta in some limit, have led to rich speculative ideas, from approaches based on strings to loop-based models. None of these have yet been confirmed experimentally. Gravity, in this sense, is a bridge between the very large and the very small that our current theories have not fully crossed. Another puzzling aspect of gravity is its relative weakness compared with the other fundamental forces. The electromagnetic interaction that governs chemistry and light, for instance, is many orders of magnitude stronger than gravity. You can easily lift a small object against the entire pull of the planet using nothing more than the muscles in your hand. Physicists refer to this as the hierarchy problem. Why is gravity so comparatively feeble? And is this telling us something deep about space-time or extra dimensions? Various models suggest that gravity might appear weak because it spreads into hidden dimensions beyond the familiar 3 of space. But so far, such ideas remain untested. When we speak about gravity in everyday settings, we usually mean the pull we feel toward Earth. In reality, both you and the Earth attract each other. Technically, the Earth also falls toward you, but because your mass is tiny compared with the planet, the motion of Earth in response to your presence is imperceptible. The same law applies universally. A distant star attracts its planets, a galaxy attracts neighboring galaxies, and even light feels the influence of gravity because space-time tells it how to travel. In orbit, astronauts experience what is often called microgravity. they are not free of gravity at all. The gravitational pull of Earth at the altitude of a typical space station is only slightly weaker than at the surface. The apparent weightlessness comes from the fact that both the astronauts and their spacecraft are in continuous free fall around the planet. They are constantly falling toward Earth, but also moving forward fast enough that they keep missing it. This state of perpetual falling creates the sensation of floating. On cosmic scales, gravity is the architect of structure. After the early universe cooled enough for matter to form, tiny variations in density collapsed under their own gravity to form the first stars and galaxies. The large-scale structure of the cosmos that we map with modern telescopes is evidence of gravity patiently sculpting matter, turning small primordial ripples into the cosmic web we see today. General relativity also predicts that when very massive objects accelerate, they create ripples in spacetime called gravitational waves. These waves carry energy away from events such as the merger of two black holes or two neutron stars. Their direct detection required exquisitely sensitive interferometers able to sense distortions of spacetime far smaller than the size of an atom, and confirmed yet another aspect of Einstein's picture, opening a new way of listening to the universe. Even with these profound insights and achievements, we are still left with conceptual questions at the frontiers of theory. Is space-time fundamental, or does it emerge from something even more basic, perhaps from patterns of entanglement and information at a microscopic level? How does gravity behave in the most extreme places, such as the interior of black holes or the very beginning of the universe? These questions are not yet answered, and they remind us that gravity is both well understood and deeply mysterious. At the human scale, though, you do not need to resolve these puzzles to feel gravity's constant presence. It is there in the way your body rests against your chair, in the quiet pull on your muscles, in the stable feeling that there's a definite down and a definite up. The same interaction that choreographs the motion of galaxies is gently holding you to the planet as you breathe. As you listen, you can let that thought become something calming. The universe is doing a simple, steady thing. Matter curves space-time, and space-time guides matter. And through that quiet interplay, you are held securely to the earth beneath you. You do not have to solve the equations tonight. You can let gravity take care of your body, keeping you grounded, while your mind slowly drifts, your muscles soften, and the weight you feel becomes a reminder that it is safe to rest and let go of the day. Chapter 2. From Newton to Einstein, How Our Understanding Evolved. The story of gravity is also the story of how humanity learned to see the universe with increasing clarity. It begins with something as ordinary as a falling stone and expands outward to the motions of planets, the bending of light, and the geometry of space-time itself. For centuries, gravity was treated as a familiar companion, something unquestioned and unquestionable. Yet, across generations of thinkers, this everyday experience slowly unfolded into one of the most profound transformations in all of science. This chapter explores how that transformation happened, moving from Isaac Newton's elegant laws to Albert Einstein's revolutionary reimagining of the cosmos. Before Newton, explanations of motion were divided. Objects near Earth behaved in one way, and objects in the heavens followed rules that seemed entirely separate. The Earth was the domain of falling bodies, projectiles, and friction. The heavens were the domain of perfect circles and divine order. The great shift came from recognizing that nature does not keep two ledgers. The same reality governs everything, from an apple drifting downward to the moon curving through the sky above. Newton provided a mathematical foundation that unified these realms. He introduced the idea that every mass attracts every other mass, and that this attraction governs motion across all scales. His formulation described the motion of planets with astonishing accuracy and offered a new explanation for the shape of cometary orbits and the rise and fall of tides. It was the first time in history that a single physical principle applied equally to stones, oceans, moons, and stars. This perspective reshaped scientific thought. It told astronomers that the universe was not arbitrary or ruled by hidden whims. Instead, it followed precise, predictable relations. With Newton's equations, one could, in principle, determine the future positions of celestial bodies with remarkable precision. This introduced an era of celestial mechanics that transformed navigation, astronomy, and physics itself. Yet even at the height of Newtonian triumph, there were puzzles lingering at the edges. Newton himself expressed discomfort with the idea that a force could act instantaneously across empty space, with no medium or mechanism connecting distant masses. He famously remarked that the notion of one body influencing another without something in between was difficult to accept. But despite the philosophical unease, the mathematics worked astonishingly well. So well, in fact, that for more than 2 centuries, Newton's view of gravity remained almost unchallenged. By the middle of the 19th century, however, cracks began to appear in the foundations. These cracks were not failures, but subtle signs that the Newtonian picture was incomplete. More accurate measurements of Mercury's orbit revealed a small discrepancy. Its elliptical path rotated slightly faster than Newton's theory predicted. The difference was tiny but persistent, and it resisted all attempts at explanation through the known gravitational influences of other planets. Meanwhile, other developments were unfolding. The study of electricity and magnetism had revealed a new kind of force, one that required fields rather than direct action at a distance. James Clerk Maxwell showed that light itself was an electromagnetic wave propagating at a universal speed. This raised a profound question. If light always travels at the same speed, regardless of the motion of its source, how can it fit within Newton's framework, where velocities add and subtract in simple ways? Physicists found themselves unable to reconcile the constancy of light with the classical picture of space and time. Into this landscape stepped Albert Einstein. As a young patent clerk, he was deeply fascinated by the puzzles surrounding light and motion. His special theory of relativity, introduced in the early 20th century, proposed that space and time are not separate entities but parts of a single fabric. It showed that measurements of length, time, and even simultaneity depend on the motion of the observer. This already suggested that something profound lay beneath the surface of everyday experience. However, special relativity did not yet include gravity. It described the behavior of objects moving at constant speeds in flat spacetime. But gravity curves the paths of falling bodies, accelerates objects, and shapes the motion of planets. Einstein began searching for a way to integrate gravity into the new relativistic worldview. His insight, built on earlier mathematical work by Bernard Riemann and others, was that gravity might not be a force at all, but instead a manifestation of curved space-time. This was the core idea of general relativity. Matter and energy distort the geometry around them, and objects move according to the straightest possible paths within that curved geometry. A freely falling object is not being pushed or pulled by a force. It is simply following the natural line of travel dictated by the shape of space-time itself. In this way, Newton's conceptual problem of action at a distance disappears. There is no mysterious pull across emptiness. The curvature of space-time acts as the intermediary. General relativity also changed how scientists understood time. In stronger gravitational fields, time itself runs more slowly. This is not a metaphor, but a measurable effect. Clocks placed at different heights tick at different rates. Even the flow of time on satellites must be corrected to match clocks on Earth's surface. Without these corrections, technologies that depend on precise timing would drift far out of alignment. One of the earliest triumphs of general relativity was its explanation of Mercury's orbit. The very discrepancy that Newton's theory could not resolve emerged naturally from the curvature around the Sun. This was compelling evidence that Einstein's picture was more complete than the one it replaced. Another prediction was that light should bend when passing near a massive object. In Newtonian gravity, this would have required a hypothetical tiny mass for light or a force acting on something without mass, both philosophically problematic. But in general relativity, the bending is a geometric effect. The path of light curves as it moves through curved space-time, just as a bead sliding along a curved wire would follow the wire's shape. Observations during a solar eclipse confirmed this bending, offering dramatic public proof of Einstein's theory. General relativity also predicted black holes, regions where space-time curves so steeply that nothing, not even light, can escape. At first, these objects were treated as mathematical curiosities. Over the decades, however, astronomical observations revealed dense remnants of collapsed stars, energetic emissions from galactic centers, and the unmistakable signatures of massive compact objects that fit perfectly with the predictions of black hole physics. The theory further predicted gravitational waves, ripples in space-time created when massive objects accelerate violently. These waves travel outward like disturbances on a pond. For many decades, they were considered too weak to detect. Yet eventually, monumental engineering efforts succeeded in measuring them directly. The faint distortions detected by large interferometers provided a new way of observing the universe, allowing scientists to hear the mergers of black holes and neutron stars across cosmic distances. Each of these successes reinforced the power of the relativity framework. Yet the story does not end here. General relativity, like Newtonian gravity before it, is incomplete. It describes gravity and space-time at large scales with extraordinary accuracy. But when applied to very small scales or extreme conditions, it clashes with quantum mechanics. Gravity refuses to fit comfortably within the quantum description that governs all other known forces. This tension motivates ongoing attempts to build a deeper theory that unifies gravity with the quantum world, an effort that continues to this day. Despite the technical details and the mathematical complexity, the evolution from Newton to Einstein represents a broader philosophical shift. Newton offered the universe as a precise machine, governed by rules that operate through forces acting over distances. Einstein, on the other hand, presented a universe in which geometry itself is dynamic. Space and time are not passive backgrounds, but active participants in cosmic evolution. They curve, stretch, and ripple in response to matter and energy. It is remarkable that the everyday sensation of weight, the pull we feel when standing still, is woven into such an intricate conceptual structure. All of this complexity reduces, in human experience, to something as simple as feeling grounded. Yet behind that simplicity lies a story of centuries of thought, observation, struggle, and discovery. From watching planets drift across the night sky to building detectors capable of sensing ripples smaller than a single proton, the search for understanding has continuously reshaped our view of reality. As you reflect on this long scientific journey, it becomes clear how each generation built on the previous one, how each theory offered both answers and new questions. Newton explained the motions of the heavens with clarity that reshaped science. Einstein revealed that even this clarity was only a surface layer, underlain by deeper structures. And yet, even Einstein's vision is not the final word. In the quiet of the evening, you might think about how these theories offer more than equations. They show that the universe is not static or simple, but layered, subtle, and vivid in ways our ancestors could never have imagined. They remind us that every understanding is a stepping stone, not an endpoint. And perhaps as you settle in, you can let that thought be comforting. The same universe that bends light and curves space-time also carries you gently through each moment. You are part of this vast story, woven into a tapestry of stars, forces, and unseen structures. You do not have to solve the mysteries tonight. It is enough to know that the cosmos is still unfolding, still revealing itself, and that you have a quiet place within it to rest. Chapter 3. Gravity as Curved Space-Time, the Modern Picture. Gravity is often introduced as a familiar pull, something that draws objects downward, holds the moon in orbit, and anchors the planets around the sun. But in the modern scientific view, gravity is not a force in the traditional sense at all. It is a manifestation of the geometry of space-time, a curvature woven into the fabric of reality itself. This idea, at the heart of general relativity, reshapes our understanding of motion, acceleration, and even time. To grasp gravity through this lens requires letting go of some intuitions and embracing a picture that is both deeper and more elegant than the classical description. At the foundation of general relativity is the recognition that space and time form a single, interconnected entity. Before this idea, space was understood as a static stage on which events unfolded, and time was viewed as a universal rhythm that beat the same everywhere. But experiments involving light, electricity, and motion revealed that these assumptions could not hold. The speed of light remained constant regardless of the observer's motion, and measurements of time and length differed depending on relative velocity. These results pointed toward a more profound structure, one in which space and time were not independent but deeply entwined. In this framework, gravity arises because mass and energy influence the geometry of space-time, and objects follow the natural paths within that geometry. These paths are called geodesics, the closest analogs to straight lines in a curved environment. This interpretation eliminates the need for gravity as a force reaching out across a distance. Instead, the presence of mass shapes the stage itself, and objects move accordingly. A common analogy is to imagine a flexible sheet representing space-time. If a heavy object rests on the sheet, it deforms the surface, creating a valley. A smaller object placed nearby will move along the curved surface toward the larger one, not because it is pulled by a force, but because the geometry itself channels its path. The analogy is imperfect, as real space-time curvature acts in more than two dimensions and affects time as well as space. But it provides an intuitive starting point. One of the profound consequences of curved space-time is the idea that gravity can slow the passage of time. Clocks situated in stronger gravitational fields tick more slowly than identical clocks in weaker fields. This phenomenon, called gravitational time dilation, has been confirmed repeatedly. It affects signals between satellites and Earth and must be accounted for in technologies that rely on precise timekeeping. In practical terms, time flows differently depending on altitude, though the differences are extremely small for everyday experience. Curved spacetime also dictates the paths that light follows. Even though light has no mass, it still travels along geodesics. When spacetime is curved, those geodesics are not straight in the usual sense, and so the path of light bends around massive objects. This bending has been observed around stars, galaxies, and clusters of galaxies. It allows astronomers to measure cosmic masses that cannot be seen directly, since the amount of curvature reveals the presence of matter, including matter that does not emit or reflect light. In more extreme environments, the curvature can be so intense that it creates regions from which not even light can escape. These regions are black holes, objects predicted by general relativity and now confirmed observationally. At their centers lies a point where the curvature becomes infinite, at least according to current theory. Surrounding that point is an event horizon, a boundary that separates what can be observed from what cannot. The existence of black holes highlights the depth of general relativity's implications. They represent limits of measurement, places where space-time folds in on itself so severely that the usual rules break down. The concept of curved space-time also explains phenomena that puzzled physicists long before general relativity emerged. For example, the precession of Mercury's orbit, where the planet's elliptical path shifts slightly with each revolution, was a persistent anomaly. Newtonian gravity could not account for the exact amount of this shift. General relativity, by contrast, predicted it precisely. The curvature near the Sun alters the shape of Mercury's orbit in subtle ways that become measurable over long periods. Another important prediction of curved spacetime is the existence of gravitational waves. These waves are ripples that propagate through spacetime when massive objects accelerate, especially in violent events such as merging black holes or neutron stars. Detecting these waves required incredibly sensitive instruments capable of measuring distortions far smaller than the width of a proton. When the first detection was made, it confirmed a century-old prediction and opened a new form of astronomy, allowing scientists to observe cosmic events that are invisible through electromagnetic radiation. Despite its success, the geometric view of gravity remains incompatible with quantum mechanics, which governs the behavior of particles at the smallest scales. Quantum theory describes interactions through quantized fields and discrete exchanges of energy, whereas general relativity describes gravity through smooth, continuous geometry. Attempts to merge these two frameworks have led to theories that propose space-time itself might have an underlying quantum structure, perhaps made of tiny loops or vibrating strings. These ideas remain unconfirmed, but they reflect ongoing efforts to reconcile gravity with the rest of physics. The modern picture of gravity also has profound implications for cosmology. If space-time curves in response to mass and energy, then the large-scale structure of the universe reflects the distribution of matter and energy across cosmic time. Observations show that the universe is expanding, and this expansion itself can be understood as a dynamic property of spacetime. The rate of expansion is influenced by the content of the universe, including ordinary matter, radiation, and the mysterious dark energy that seems to accelerate the cosmic expansion. The curvature of the universe on the largest scales helps determine its fate, whether it continues expanding indefinitely, slows and stabilizes, or eventually recollapses. Because mass and energy shape spacetime, and spacetime guides motion, the interplay between geometry and matter becomes the central theme of the modern gravitational picture. This interplay leads to predictions that extend far beyond the classical view. It explains gravitational redshift, where light climbing out of a gravitational well loses energy and shifts to longer wavelengths. It explains how rotating massive bodies can drag spacetime around with them, a phenomenon called frame dragging. It shows why objects in free fall experience no gravity locally, even though they are moving through curved spacetime. In daily life, the curvature of spacetime is so slight that it feels like an invisible background. Our surroundings appear flat, and time seems to flow at a steady pace. The gravitational pull we feel is a manifestation of geometry, but the curvature required to produce noticeable distortions is far beyond human perception. Still, those distortions exist everywhere, shaping the trajectories of planets, the evolution of galaxies, and the path of the universe itself. Even the act of standing still on Earth's surface involves a subtle acceleration upward from the ground, as spacetime guides objects along paths they would otherwise follow freely. Understanding gravity as curved spacetime invites us to rethink not only motion, but the very meaning of straightness, direction, and flow. A straight line in this context is not defined by intuition, but by the geometry of the world. When an astronaut orbits Earth, they are not floating aimlessly. They are following a geodesic in curved spacetime. When light bends around a galaxy, it is not being tugged, but traveling naturally through a warped landscape. When we step back, this modern picture shows us that gravity is a story told by the universe through its shape. Mass and energy leave imprints on spacetime, and those imprints guide everything that moves. It is a quiet, continuous conversation between matter and geometry, one that unfolds across every moment and every corner of the cosmos. As you reflect on this, there's a sense of profound connection. The same curvature that guides galaxies across eons is also the gentle structure that holds you to the Earth. You are part of this vast tapestry of spacetime, shaped by forces older than stars and quieter than light. In the stillness of this moment, it is possible to feel small yet deeply rooted, moving through a universe whose geometry cradles you as surely as it shapes everything else. And in that realization, there is a quiet comfort, a reminder that you belong to something expansive, intricate, and endlessly unfolding. Chapter 4. Why Gravity is So Weak, the Hierarchy Problem. Gravity shapes the grandest structures in the universe. It draws planets into orbit, organizes stars into galaxies, and sculpts the evolution of cosmic clusters stretching across millions of light years. Yet at the scale of human life, gravity is startlingly weak. A small magnet can lift a metal pin against the gravitational pull of an entire planet. Your own muscles can momentarily overcome the force that governs the structure of the cosmos. This enormous contrast, between the strength of gravity and the strengths of the other fundamental interactions is known as the hierarchy problem. It is not simply an odd numerical mismatch. It is one of the most profound open questions in modern physics. To understand why this question matters, one must first appreciate how unusual gravity is among the fundamental interactions. The electromagnetic, weak, and strong interactions are described by the quantum framework of the Standard Model, a theory that has been tested with extraordinary success in laboratories around the world. These interactions all operate with strengths that, although different, lie within a broad and comprehensible range of values. Gravity, by contrast, sits far outside this range. Its strength is so much smaller than the others that, in the quantum picture, it effectively disappears at the microscopic scale. Two protons repel each other electromagnetically with a force so large compared with their gravitational attraction that the latter is essentially irrelevant in any calculation involving atomic or molecular structure. This is the heart of the mystery. If the fundamental interactions arise from the same underlying laws of nature, why does one of them appear so extraordinarily feeble? Why do the scales associated with gravity differ so drastically from the scales associated with the other interactions? Why does gravity become noticeable only when vast amounts of matter are involved? The question becomes sharper when considering the concept of energy scales. In quantum field theory, each interaction has an associated characteristic scale that determines when quantum effects become significant. For electromagnetism and the other interactions in the Standard Model, these scales lie comfortably within ranges accessible, at least in principle, to high-energy particle experiments. Gravity's characteristic scale, however, is unimaginably higher, so high that it is far beyond anything current or foreseeable experiments can reach. This enormous separation is the essence of the hierarchy problem. The universe contains two dramatically different sets of scales, and the reason for this separation remains unknown. Classical theories offer little help. In Newtonian gravity, the strength of the gravitational interaction depends on mass and distance, but there is nothing in the theory that explains why gravity should be so much weaker than the other known interactions. Newton's formulation describes how gravity behaves, but it does not tell us why it possesses its particular strength or why that strength should differ so dramatically from the strengths of other interactions. Classical physics simply accepts gravity's weakness as a given. General relativity, the modern geometric description of gravity, reframes the problem but does not solve it. In this theory, mass and energy curve spacetime, and gravity arises not as a force but as a consequence of this curvature. The amount of curvature produced by a given mass reflects gravity's strength, but nothing in the equations of general relativity explains why the curvature generated by ordinary matter is so small. The theory provides a tremendously successful description of how spacetime reacts to mass, but it offers no insight into why the intrinsic coupling between mass and curvature is so tiny compared with the couplings involved in particle physics. The difficulty deepens when one attempts to bring quantum mechanics into the picture. The Standard Model describes the other interactions in terms of quantized fields, with forces mediated by particles that carry specific properties. Gravity, when treated in the same way, does not fit neatly into this framework. If one tries to quantize gravity similarly, the resulting theory becomes problematic at high energies. The The scale at which quantum gravitational effects become important is vastly larger than the scales associated with the other interactions. This enormous gap implies that, in the quantum sense, gravity is suppressed by a factor so extreme that it is effectively invisible at ordinary energies. Several ideas have been proposed to explain this disparity, and one of the most intriguing involves the possibility of extra dimensions. If gravity can spread into spatial dimensions beyond the familiar three, its apparent weakness in our observable world could be an illusion. In such models, the true strength of gravity might be comparable to the strengths of the other interactions, but because part of its influence escapes into additional dimensions, we observe only a diluted version. This would mean that the gravitational field lines spread into a larger space than the other interactions, weakening the effect we feel. Although elegant, these models remain speculative. Experimental searches for signatures of extra dimensions. For example, deviations from expected gravitational behavior at extremely small scales have so far found no conclusive evidence. Another line of thought suggests that gravity may not be fundamental at all, but instead emergent. In this view, gravity arises from deeper microscopic processes, much like temperature arises from the motion of atoms. If spacetime and gravity emerge from underlying quantum information, or from collective behavior of more fundamental entities, then gravity's weakness might reflect the way large-scale structures arise from smaller-scale dynamics. Under this interpretation, the gravitational interaction is a macroscopic phenomenon, inherently weaker because it emerges from averaging or collective processes rather than from direct fundamental couplings. While conceptually attractive, this idea remains an open question, with no experimental confirmation yet available. There are also approaches that attempt to modify the structure of the standard model itself to accommodate gravity's weakness. Some theories suggest that symmetries or hidden mechanisms protect the strength of the other interactions while leaving gravity unaffected. Others propose that gravity's weakness may be tied to the vacuum structure of spacetime, perhaps reflecting relationships between dark energy, quantum fluctuations, and the geometry of the universe. These ideas, while mathematically rich, are still under investigation and have not yet converged on a definitive solution. The hierarchy problem also touches on cosmology. In the early universe, when temperatures and energies were unimaginably high, the contrast between gravitational and non-gravitational interactions may have arisen from processes that took place during inflation or immediately afterward. Observations of the cosmic microwave background and the distribution of galaxies are providing increasingly precise windows into these early epochs. Yet so far, nature has kept its deeper secrets well hidden. Despite the many attempts to solve it, the hierarchy problem remains open. Its persistence is a sign that something fundamental about the structure of nature is not yet understood. It is a reminder that our theories, powerful though they are, may only describe a surface layer of a deeper reality. This is why the hierarchy problem is considered one of the central clues in the search for new physics. It suggests that gravity's weakness is not simply an accident of nature, but a reflection of principles not yet discovered. And perhaps this is where the question becomes not only scientific, but philosophical. The universe is arranged in such a way that the weakest interaction governs the largest structures. The gentlest of forces shapes galaxies, regulates cosmic evolution, and anchors each of us to the world. In the quiet of these reflections, it becomes clear how intricate the cosmos truly is. Something so faint, so easily overcome by a human hand, still holds the stars in their orbits. And as you sit with that thought, you might feel a sense of connection to a universe woven from subtleties. A universe where even the smallest strength can shape the greatest expanse, and where your own existence rests within that delicate balance. Chapter 5. What anti-gravity really means. The term anti-gravity has lived in the human imagination for a long time. It suggests a technology or phenomenon that cancels gravity, reverses it, or makes objects float freely without support. In science fiction, anti-gravity often appears as a propulsion system, a hovering platform, or an effortless way to defy the pull of a planet. But in modern physics, the concept is far more subtle, far more intricate, and deeply tied to the structure of spacetime itself. To understand what anti-gravity really means, one must step carefully through what gravity actually is and what it is not. In everyday language, gravity seems like a force that pulls downward. We experience it as weight, as the feeling of pressure in our muscles, as the downward arc of falling objects. But in the modern scientific picture, gravity is not a pull at all. It is the curvature of space-time created by mass and energy. Objects in free fall are not being tugged. They are simply following geodesics, the natural paths embedded in curved geometry. This understanding, central to general relativity, changes the meaning of anti-gravity. If gravity is not a force, then anti-gravity cannot be a force of equal magnitude in the opposite direction. Thus, the first scientific insight is this: genuine anti-gravity, in the strictest sense, does not exist within known physics. There is no companion interaction that cancels space-time curvature the way electrical charges can cancel one another. There is no negative gravity particle corresponding to positive and negative charges. Curved spacetime is shaped by mass and energy, and its geometry is always attractive in the sense that it draws matter and light inward. This has been confirmed across many scales, from falling apples to orbiting planets to galaxies bending the paths of distant starlight. However, this does not mean that there are no physical processes that resemble anti-gravity or that create effects which, to an observer, appear to counteract gravity. The key is understanding how general relativity allows spacetime to behave and how certain forms of energy influence curvature differently from ordinary matter. One of the most important of these forms is the energy associated with the vacuum itself, which in cosmology is linked to dark energy. Dark energy behaves in a way that effectively produces a repulsive gravitational effect on cosmic scales. It does not cause objects to float locally. Instead, it drives the expansion of the universe, causing galaxies to recede from one another at ever-increasing rates. This expansion is not the result of a force pushing galaxies apart, but a property of spacetime undergoing accelerated stretching. In this subtle sense, dark energy acts like an anti-gravitational component of the universe. It increases the distance between large structures over time because it generates a form of curvature that opposes the attractive effects of ordinary mass. But dark energy is diffuse and extremely weak on local scales. It cannot lift a rock, float a spacecraft, or counteract the gravity of Earth in any noticeable way. Its influence only becomes significant when applied across truly immense cosmic distances. Another concept that arises in discussions of anti-gravity is the idea of negative mass. In general relativity, Mass and energy determine the curvature of space-time. If there were matter with negative mass or negative energy density, it would create curvature with properties opposite those produced by ordinary matter. Objects near negative mass would accelerate away from it in behavior that closely resembles the popular notion of anti-gravity. However, no known particles possess negative mass, and there is no experimental evidence for such matter existing anywhere in the observable universe. Some theoretical models allow for the mathematical possibility of negative energy densities in extremely small regions, often associated with quantum fields. These effects are tied to phenomena like the Casimir effect, where quantum fluctuations produce forces that can resemble negative energy under certain interpretations. However, these regions are tiny, transient, and tightly constrained. They cannot be used to levitate objects, cancel planetary gravity, or produce stable, macroscopic anti-gravitational behavior. They remain interesting theoretical tools, but not practical mechanisms. Another scientific context where anti-gravity is sometimes discussed is in relation to hypothetical faster-than-light propulsion systems, such as the Alcubierre warp metric. In these speculative ideas, space-time is manipulated in ways that allow a region to move without locally exceeding the speed of light. These constructs require exotic energy conditions, including negative energy densities, and would involve manipulating space-time itself rather than opposing gravity directly. But these ideas remain purely theoretical. They require forms of matter not yet observed and energy conditions that violate known physical constraints. Outside of general relativity, there are classical phenomena that appear to mimic anti-gravity even though they do not involve modifying space-time at all. Magnetic levitation, diamagnetism, superconducting pinning, and radiation pressure can all lift or suspend objects in ways that defy gravity's pull. For example, certain materials can be levitated above powerful magnets due to repulsive interactions between electron orbitals and magnetic fields. Superconductors can trap magnetic field lines and produce stable hovering effects that feel eerily close to anti-gravity. Similarly, intense beams of light can exert pressure strong enough to push objects in microgravity environments. But these effects are not gravitational in origin. They rely on electromagnetic forces or quantum properties that overwhelm gravity at small scales. This distinction is important. These levitation mechanisms are not examples of anti-gravity, but rather demonstrations of other interactions overpowering gravity. They do not cancel gravity, they simply exceed it. The scientific meaning of anti-gravity becomes clearer when one remembers that general relativity allows for many ways to manipulate space-time curvature. Gravity is not a uniform field that must be canceled. It is a geometric phenomenon that responds to mass, energy, and momentum. In principle, if one could rearrange energy densities or engineer exotic forms of matter, one could produce local curvature with unusual properties. But none of this is possible with known materials or known technologies. The universe provides no naturally occurring regions where gravity reverses direction, and no laboratory experiment has ever produced a gravitational repulsion of this kind. It is also worth noting that the phrase gravitational shielding, sometimes invoked in popular culture, has no basis in modern physics. Gravity cannot be blocked, screened, or reflected in the way that electromagnetic fields can be shielded. Because gravity is curvature, shielding would require altering space-time geometry itself. All experiments designed to detect gravitational shielding have found nothing, reinforcing the view that gravity interacts universally with all forms of mass and energy. Still, the search for new physics continues, and it is not impossible that future discoveries could reveal mechanisms that mimic anti-gravity more closely than anything currently known. If negative mass or exotic energy conditions were discovered, they could open pathways to gravitational manipulation far beyond current science. If quantum gravity ultimately reveals a deeper layer of structure, it might contain principles that transform our understanding of curvature itself. At present, however, nature has not shown us any form of true anti-gravity. And yet, even without such a phenomenon, the discussion of anti-gravity illuminates the beauty of the scientific picture we do have. It shows how deeply interconnected mass, energy, geometry, and motion truly are. It reminds us that even the search for what does not exist can reveal the intricacies of what does. As you reflect on this, consider how strange and elegant the universe is. A simple downward pull is not a pull at all, but the whisper of space-time shaping your path. The idea of anti-gravity, though elusive, reveals the depth of our curiosity and the endless layers of reality still waiting to be uncovered. And in that vast unknown, in the quiet interplay of forces and geometry, there is room for wonder, and for you, drifting gently through a cosmos far more mysterious than it first appears. Chapter 6. Dark Energy, the universe's real repulsive force. When we speak of gravity, we usually imagine a force that draws objects together, a gentle but persistent attraction that shapes the architecture of the cosmos. For centuries, this was the only gravitational influence anyone knew. Everything in the universe seemed bound by this quiet pull. Stars gathered into galaxies, galaxies gathered into clusters, and clusters into vast webs stretching across cosmic space. It was natural to assume that as the universe aged, gravity would gradually slow the expansion that began in the aftermath of the Big Bang. Galaxies would drift apart more slowly over time. The expansion might eventually halt or even reverse if gravity's collective pull became strong enough. But observations at the end of the 20th century produced a profoundly unexpected result. Instead of slowing, the expansion of the universe is speeding up. Galaxies are receding from one another more quickly now than they were in the past, and this acceleration appears to be increasing. The discovery shocked cosmologists because nothing in the standard picture of matter or energy predicted such behavior. To explain this cosmic acceleration, scientists introduced a concept known as dark energy, a mysterious form of energy that permeates all of space-time and creates a repulsive gravitational effect on the largest scales. Understanding dark energy requires first understanding how general relativity describes gravity. In Einstein's framework, mass and energy determine the curvature of space-time, and this curvature guides the motion of matter and light. Importantly, it is not only mass that shapes curvature. Pressure and energy density also contribute. Most familiar forms of matter generate attractive curvature, meaning they draw objects together. But if a particular kind of energy has an unusual pressure, specifically a large negative pressure, it can create curvature that leads to an accelerated expansion. This is the key to understanding how dark energy behaves like a repulsive gravitational component. One of the simplest interpretations of dark energy is the cosmological constant, a term Einstein originally introduced into his equations. He intended it to counterbalance gravitational attraction and maintain a static universe. Later, when it became clear that the universe is expanding, Einstein reportedly called the cosmological constant his greatest mistake. Yet long after he abandoned it, the term resurfaced as a possible explanation for cosmic acceleration. The cosmological constant can be interpreted as the energy of empty space itself. Even in the absence of matter, space-time may contain an intrinsic energy density that remains constant everywhere and at all times. This vacuum energy has an extraordinary property. It exerts a negative pressure. In general relativity, negative pressure contributes to the curvature of space-time in a way that drives expansion. Instead of pulling matter together, it causes space to stretch faster. The more space expands, the more dark energy it contains, since its density does not dilute in the way matter or radiation do. This creates a self-sustaining acceleration that gradually dominates the dynamics of the cosmos. Observational evidence strongly supports the existence of dark energy. Measurements of distant supernovae reveal that these exploding stars appear dimmer than expected, consistent with accelerated expansion. Observations of the cosmic microwave background provide a snapshot of the early universe, and the patterns in this ancient light show that the amount of matter present cannot account for the observed geometry of space. Large-scale surveys of galaxies map how cosmic structures grew over time, and these maps indicate that something is counteracting gravity's ability to pull matter together. Independent lines of evidence all point to a universe where dark energy makes up most of the total energy content. Despite this, the nature of dark energy remains deeply mysterious. If it is simply vacuum energy, then we face a new puzzle. Theoretical calculations of vacuum fluctuations predict a value vastly larger than what is observed. The difference between the predicted and measured values is so enormous that it represents one of the biggest discrepancies in theoretical physics. This tension suggests that our understanding of quantum fields, gravity, or space-time, or all of them, may be incomplete. Other possibilities have been proposed. Some theories suggest that dark energy is not a constant, but a dynamic field that evolves slowly over time. Such fields would contribute varying amounts of energy depending on cosmic age, potentially altering the rate of expansion in subtle ways. These models can mimic the behavior of a cosmological constant while offering flexibility to address the discrepancy in vacuum energy calculations. However, no experimental evidence has yet confirmed such fields. There are also ideas that attempt to modify general relativity itself on very large scales. In these models, the observed acceleration is not caused by a new form of energy, but by changes in how gravity behaves at cosmic distances. These theories propose that spacetime may have additional geometric properties, or that the equations describing its curvature must be adjusted beyond a certain threshold. While mathematically compelling, such modifications must be handled carefully to remain consistent with the precise tests of gravity conducted within the solar system and the behavior of gravitational waves recently observed. As of now, no alternative theory has matched the broad success of general relativity while also accounting for accelerated expansion. Another intriguing possibility is that dark energy is related to the structure of spacetime at the quantum level. If spacetime has a granular or information-based structure, the dynamics of this underlying substrate might produce effects that appear as dark energy on large scales. This line of thinking connects to attempts to unify gravity with quantum mechanics, suggesting that cosmic acceleration could provide a rare window into physics that lies beyond current theories. But this remains highly speculative and untested. Regardless of its origin, dark energy has profound implications for the future of the universe. As expansion accelerates, galaxies move farther apart at ever-increasing speeds. Over immense cosmic timescales, distant galaxies will slip beyond the cosmic horizon, disappearing from view as their light can no longer reach us. The universe will become increasingly isolated, with each gravitationally bound structure drifting into solitude. If dark energy remains constant, the universe will grow colder, emptier, and more diffuse as time stretches toward an unending future. If dark energy increases over time, even more dramatic fates become possible, including scenarios where space-time itself is eventually torn apart. If it decreases, the acceleration may slow or cease, potentially allowing gravity to reassert itself. But current observations suggest that dark energy is not changing significantly, pointing toward a future of continued acceleration. The study of dark energy is a reminder of how little we truly know about the universe. A century ago, the idea that empty space could push galaxies apart would have seemed absurd. Even today, the mechanism behind this cosmic repulsion remains elusive. Yet we accept its presence because the evidence is overwhelming, woven into the fabric of light from the earliest eras of cosmic history. In this sense, dark energy challenges not only scientific theories, but human intuition. It forces us to question what it means for space to expand and what it means for the universe to evolve. It blurs the line between emptiness and substance, showing that even a vacuum can shape the destiny of galaxies. And perhaps there is something quietly profound in that. The universe is driven not only by the visible things, stars, planets, and glowing nebulae, but also by the invisible, the subtle, the silent. Dark energy, unseen and unfelt, shapes the fate of everything. It reminds us that reality is deeper than appearance, that much lies hidden beneath the surface of what we can measure or imagine. And as you let your thoughts drift across these vast distances, you may sense a calm awareness that you too exist in a universe full of mystery. A universe that expands gently around you, carrying you forward through time on currents older than stars. Chapter 7. Negative mass and exotic matter. Could they exist? Among the most fascinating possibilities permitted by modern theoretical physics is the idea that matter might exist with properties radically different from anything encountered in everyday experience. Chief among these hypothetical forms is negative mass, a concept that seems almost paradoxical, yet is mathematically consistent within certain interpretations of general relativity and quantum field theory. Closely related is the broader idea of exotic matter, a catch-all term for forms of matter or energy that violate classical expectations or behave in non-standard ways. Though no confirmed observations of such matter exist, the study of negative mass and exotic energy conditions opens a window into what the universe might allow at its deepest levels. To begin, consider what mass represents in conventional physics. In classical mechanics, it measures inertia, the resistance of an object to acceleration. In Newtonian gravity, mass determines how strongly objects attract one another. General relativity deepens this notion. Mass, along with energy, pressure, and momentum, becomes part of the stress-energy tensor, the source of the curvature of space-time. Everything that possesses energy contributes to shaping space-time, and the resulting curvature determines how objects move. If negative mass existed, it would enter these equations with the opposite sign. The consequences are surprising. A negative mass would contribute negative energy density to spacetime, potentially creating curvature opposite to that produced by ordinary matter. In simple thought experiments, a negative mass pushed by a positive mass could accelerate in unexpected ways. Because negative mass would carry negative inertia, it could respond to pushes or pulls by accelerating opposite to the applied force. Although such behavior is mathematically allowed, it has never been observed in nature. No known particle or astrophysical structure exhibits these properties. Despite this lack of evidence, theoretical discussion of negative mass has persisted because of the role it plays in speculative space-time geometries. Some of the most dramatic solutions of general relativity, including traversable wormholes and certain kinds of warp-like distortions, require regions where the stress-energy content of spacetime behaves unusually. These solutions demand matter that violates classical energy conditions, which describe how mass and energy should behave under normal circumstances. The existence of exotic matter, therefore, is not a frivolous idea, but a necessary ingredient in the mathematics of some hypothetical spacetime structures. Energy conditions are assumptions designed to keep spacetime solutions physically sensible. They ensure that mass and energy densities remain non-negative, that energy flows in plausible directions, and that matter does not create unphysical behavior. Yet there is no requirement that nature must respect these conditions in all circumstances. They reflect our expectations about ordinary matter, not the full range of what might be possible. Violating these conditions does not necessarily break physics. It merely pushes into a territory where intuition becomes unreliable. Quantum field theory, which governs the world of particles and fields, complicates the picture. Although no particle with negative mass has ever been observed, quantum fields can produce effective regions of negative energy density. One well-known example is the Casimir effect, where the arrangement of conducting plates modifies the vacuum fluctuations of quantum fields in such a way that the energy between the plates becomes lower than the energy in the surrounding space. Technically, this is not negative mass, but it demonstrates that the vacuum energy can be manipulated into regimes that classical physics does not allow. These negative energy regions are fleeting, tiny, and tightly constrained, but they show that quantum fields can briefly violate classical energy conditions. In this sense, exotic matter need not consist of actual particles with negative mass. It may instead refer to exotic states or configurations of energy that deviate from ordinary expectations. These states could exist only for extremely short durations or under extreme conditions, such as those near black holes or in the early universe. The challenge is determining whether such exotic energy conditions can ever become stable enough to produce macroscopic effects. The idea of negative mass also intersects with cosmology. The accelerated expansion of the universe suggests the presence of dark energy, a form of energy that produces repulsive gravitational effects on cosmic scales. Dark energy, however, does not behave like negative mass in the classical sense. It has positive energy density, but exerts negative pressure, which leads to the accelerated expansion. It does not clump, does not form structures, and cannot be harnessed to create local anti-gravitational effects. Still, the behavior of dark energy encourages speculation about whether other exotic forms of energy might exist with different properties. Even more speculative are models in which space-time itself possesses microstructure. In these approaches, gravity emerges from quantum states of an underlying system rather than being fundamental. If space-time arises from interactions among more basic entities, then exotic matter might be a sign of unusual configurations within that underlying fabric. Negative mass could reflect a kind of topological defect or an inversion of a deeper property of space-time. These ideas remain firmly theoretical and lack experimental confirmation, but they demonstrate how negative mass might arise in frameworks very different from conventional physics. There have also been attempts to simulate negative mass behavior using condensed matter systems. In certain ultra-cold atomic gases, interactions can be engineered so that the collective behavior of the atoms mimics aspects of negative inertia. Under specific conditions, disturbances in the gas respond to pushes as though they possess negative effective mass. These systems do not contain real negative mass. Rather, they use the controlled environment of quantum fluids to reproduce some of its mathematical behavior. Such experiments help physicists understand what negative mass would look like if it were real, and they demonstrate that the equations describing negative mass are internally consistent, even if nature does not provide it. Another motivation for exploring exotic matter is the search for stable wormholes or warp-like metrics. Traversable wormholes require exotic matter to counteract the strong curvature that would otherwise close the throat of the wormhole. Without negative energy densities or similar exotic effects, wormholes collapse too quickly for anything to pass through. Likewise, hypothetical warp metrics require exotic energy configurations to sustain the distortion of spacetime around a moving bubble. These ideas remain in the realm of speculation, but they illustrate why the concept of exotic matter continues to attract interest. Despite these theoretical possibilities, the observational picture remains clear. No astrophysical object behaves as though it contains negative mass. Gravitational lensing, galaxy rotation curves, cluster dynamics, and cosmic microwave background measurements all align with models involving positive mass and ordinary gravitational attraction. The universe, as far as we can observe, respects the classical energy conditions on macroscopic scales. If exotic matter exists, it must be extremely rare or confined to regimes that are not currently accessible to observation. Still, the study of negative mass and exotic matter is valuable because it tests the boundaries of space, time, and energy. By exploring what the equations allow, physicists learn more about the constraints that nature imposes. Exotic matter challenges our assumptions about stability, causality, and energy flow. It sits at the intersection of general relativity, quantum theory, and cosmology, three fields that remain imperfectly unified. And perhaps there is an existential resonance in this exploration. The universe is not only shaped by what exists, but also by what does not. Negative mass may remain forever hypothetical, but its absence helps define the cosmic order that allows stars to form, galaxies to endure, and life to arise. Exotic matter remains a possibility on the far edges of theory, a reminder that reality is both generous and restrained, offering just enough complexity to fascinate, but not so much chaos as to overwhelm. In the quiet reflection of these ideas, you might feel the vastness of everything that could be and the extraordinary precision of what is. You are a small part of a universe balanced on the boundary between the possible and the actual, wandering through ideas that stretch beyond experience. And in that space, between imagination and reality, you find a calm awareness that the cosmos is deeper, stranger, and more beautiful than it first appears. Chapter 8. Can we shield gravity? Why it seems impossible. To understand why gravity cannot be shielded in the way we shield light, sound, or electric fields, we first need to understand what gravity truly is. In the classical view, gravity appears to be a force that acts downward, pulling objects toward Earth. This perspective encourages the intuition that perhaps gravity is something emitted by massive objects, something that might be intercepted or blocked the way a lead wall blocks radiation or the way a Faraday cage blocks electric fields. But in the modern scientific picture, gravity is not a stream of particles radiating outward. It is a manifestation of the geometry of space-time itself. Blocking gravity would require blocking geometry, and that simple statement reveals why the task seems impossible. General relativity describes gravity not as a force, but as curvature. Mass and energy determine how space-time bends, and that curvature dictates how objects move. A freely falling object is not being pulled. It is following the natural path laid out by the geometry around it. This is why astronauts orbiting Earth feel weightless, even though Earth's gravity is nearly as strong there as it is on the ground. They are in continuous free fall, following the curvature of space-time on a path that constantly misses the planet. Gravity is not a field that pushes or pulls. It is the shape of the stage on which everything unfolds. To shield gravity, therefore, one would need something capable of altering space-time curvature in a localized region, preventing the curvature caused by an external mass from reaching that region. This would be equivalent to building a barrier that instructs space-time. You may curve outside this zone, but you may not curve within it. Such a barrier has no known physical foundation. Space-time does not propagate curvature like a signal that can be absorbed or reflected. It simply is the geometric relationship that results from the distribution of mass and energy. This distinction separates gravity from all the other fundamental interactions. Electromagnetism, for example, is mediated by photons, and the presence of charges determines how electromagnetic fields develop in space. But electromagnetic fields can be manipulated, canceled, or screened. Opposite charges can neutralize each other, and conductive materials can redirect electric fields. Even the strong nuclear interaction, while extremely powerful at short distances, falls to zero beyond a certain range. Gravity, by contrast, cannot be canceled by opposite mass because there is no such thing as negative gravitational charge. Mass is always positive in the classical sense, so gravitational fields always reinforce one another. This universality is one of the reasons gravity dominates on large scales despite being weaker than the other interactions. The fact that mass is always positive also means there is no gravitational equivalent of a Faraday cage. A Faraday cage works because electric charges inside a conductor rearrange themselves to cancel external fields. But since there is only one kind of mass and it cannot be rearranged into positive and negative distributions, there is no known mechanism through which matter could naturally block or cancel gravitational curvature. Attempts to conceptualize gravitational shielding often rely on analogies with materials that filter or reflect other kinds of waves. For instance, one might imagine a substance that absorbs gravitational effects or reflects them the way mirrors reflect light. But gravitational curvature is not a wave traveling through a medium. Although gravitational waves do propagate through space-time, they represent ripples in curvature created by accelerating masses, not the static curvature produced by standing mass energy. Shielding static curvature would require manipulating the relationship between space-time and matter itself. Historically, some scientists have explored whether gravitational shielding might occur in extreme environments or through exotic materials. Experiments have tested whether superconductors might interact unusually with gravity, or whether rotating superconducting rings could create small gravitational anomalies. None of these experiments produced reproducible results, and the scientific consensus is that no material, conventional or exotic, can block gravity in any meaningful way. Part of the difficulty arises from the equivalence principle, a cornerstone of general relativity. The equivalence principle states that gravitational mass, the property that determines how strongly gravity acts on an object, is identical to inertial mass, the property that determines how much an object resists acceleration. If gravity were something that could be shielded, one would expect gravitational mass to be alterable without affecting inertial mass. But experiments have repeatedly confirmed that these two masses are indistinguishable to extraordinary precision. This means any hypothetical shield that interfered with gravity would also have to modify inertia itself, fundamentally changing the behavior of matter. No known physical mechanism allows such a separation. Even if exotic matter with negative mass existed, as explored in prior chapters, gravitational shielding would still face challenges. A negative mass near a positive mass would not cancel gravitational effects in a local region. Instead, it would alter the curvature in complex ways that might create additional instabilities. Exotic matter could, in principle, create regions of repulsive curvature, but such curvature does not block attractive curvature from external regions. It simply adds new curvature patterns. Analogous to competing hills and valleys, adding a repulsive bump to spacetime would not flatten an attractive valley created elsewhere. It would merely superimpose a second feature onto the existing geometry. There is also the issue of energy. Any system that attempted to manipulate spacetime curvature would require extraordinary amounts of energy. Even small changes in curvature require masses or energy densities far beyond anything achievable with current technology. The curvature generated by Earth, which holds us to the ground, corresponds to enormous mass energy content. Overcoming that curvature to create even a small gravitational bubble would require energies that dwarf anything humanity can produce. This understanding does not imply that gravity is entirely unchangeable. Gravity can be manipulated indirectly by moving matter around. Constructing a massive shell around an object modifies the gravitational environment inside the shell, but the field inside is not shielded. It is simply redistributed according to the shell's mass distribution. A shell can cancel the gravitational field inside it only if the shell is perfectly symmetric and massive, but such cancellation is not shielding in the usual sense. It does not prevent external curvature from reaching the interior. Rather, it produces curvature of its own that happens to sum to zero at the center. Moreover, the region outside the shell remains unaffected. So this technique cannot provide general shielding or protection from external gravitational influence. Cosmology provides further insight. The expansion of the universe is driven by dark energy, a form of energy that produces repulsive gravitational behavior on cosmic scales. Yet even dark energy does not shield gravity. It operates uniformly throughout spacetime, counteracting gravitational attraction only at immense distances and only by altering the overall dynamics of expansion. Dark energy does not create local anti-gravity zones where objects float freely. It simply changes the rate at which the universe expands. The existence of dark energy, therefore, teaches us that repulsive curvature is possible, but not that gravitational curvature can be blocked. In theoretical models that propose extra dimensions, gravity may spread into additional spatial directions, diluting its apparent strength in our three-dimensional world. This idea provides an explanation for gravity's weakness, but it does not offer shielding. Even in these models, space-time curvature is fundamental and cannot be blocked. It simply extends into more dimensions than we can observe. The impossibility of gravitational shielding thus arises from gravity's geometric nature, the equivalence of gravitational and inertial mass, the absence of negative mass, and the universal coupling of gravity to all forms of energy. These principles combine to make gravity unique among the interactions, universally attractive, geometrically embedded, and impossible to screen. And yet, in that impossibility, there is a quiet beauty. Gravity cannot be shut out or turned away. It binds the cosmos together, from stars to galaxies to the structure of space-time itself. As you reflect on this, you may sense a deeper metaphor, that some realities in life, like gravity, cannot be blocked or avoided. They simply are, shaping your path gently, persistently, with a force that is everywhere and inescapable. And there is comfort in that certainty, in knowing that the same curvature that guides the motion of galaxies also holds you lightly to the world beneath your feet, as the universe unfolds around you in its vast and steady rhythm. Chapter 9. Levitation without anti-gravity, tricks nature already uses. When most people imagine levitation, they picture an object floating effortlessly in midair, free from the pull of gravity. The idea evokes images of science fiction vehicles hovering above the ground or futuristic devices that drift silently through space. Because gravity is so constant and so difficult to overcome, levitation feels almost supernatural. But nature already provides many ways to make objects float, rise, hover, or remain suspended without ever violating the laws of gravity. These phenomena do not cancel gravity. Instead, they use other forces, often subtle, sometimes powerful, to counteract or exceed gravitational pull. Understanding these mechanisms offers insight into both the ingenuity of nature and the rich interplay of forces that shape the physical world. To begin, it is important to clarify that levitation is not anti-gravity. When an object appears to float, gravity is still acting on it with full strength. The object remains immersed in the curvature of space-time created by Earth. What changes is that another force or effect provides an upward push that balances the downward weight. In this sense, levitation is a dynamic equilibrium, a momentary or sustained balance achieved through interactions that have nothing to do with altering gravity itself. While gravity cannot be blocked or canceled, many forces in nature are strong enough, under the right conditions, to counteract it. One of the most dramatic examples of natural levitation is magnetic levitation. Magnetism is a powerful interaction arising from the behavior of electric charges and quantum spins. In the case of ferromagnetic materials or strong permanent magnets, magnetic fields can easily exceed the force of gravity acting on small objects. A magnet can hold a metal object suspended beneath it, but more interestingly, certain configurations allow objects to float above magnetic sources. In controlled laboratory conditions, magnetic fields have been used to levitate droplets of water, living organisms such as small frogs, and even small pieces of fruit. These levitation feats rely on the fact that magnetic fields exert forces on electrons within materials, and these forces, when properly arranged, can counteract gravity. Another form of levitation involves diamagnetism, a property present to some extent in all materials. Diamagnetic materials create their own magnetic fields in opposition to applied magnetic fields. In most cases, the effect is extremely weak, but in materials with strong diamagnetic response, such as pyrolytic graphite, the repulsion is strong enough to lift small shapes when placed above a suitable arrangement of magnets. This is not anti-gravity. It is the electromagnetic interaction dominating over gravity at a small scale. Gravity is incredibly weak compared with other fundamental forces, which is why even modest magnetic fields can support objects against it. The most striking form of magnetic-related levitation occurs in superconductors. When certain materials are cooled to extremely low temperatures, they enter a superconducting state in which they expel magnetic fields. This effect, known as the Meissner effect, forces magnetic field lines to bend around the superconductor. When a magnet is placed near a superconductor, the interaction can produce stable levitation, with the magnet hovering motionless in midair. Under specific conditions, superconductors can lock magnetic fields in place, creating what is known as flux pinning. This allows objects to hover not only above a magnet, but to remain fixed in almost any position relative to it, maintaining stability even when moved or rotated. This phenomenon has inspired visions of frictionless transportation and near-effortless suspension systems. Levitation can also arise from aerodynamic forces. Birds, airplanes, and gliders stay aloft not by canceling gravity, but by using the flow of air to generate lift. Bernoulli's principle and Newtonian reaction forces combine to create upward pressure differences that counteract weight. Although this form of levitation requires constant motion, it demonstrates that the natural world is full of strategies for resisting gravity without altering its underlying cause. Even seeds, such as those of the dandelion, use intricate structures to create tiny vortices in the air, allowing them to drift for remarkable distances. In still another example, buoyancy allows objects to float in fluids. A balloon rises in air because the surrounding atmosphere exerts greater pressure on its lower surface than on its upper surface. A boat floats because the weight of the water it displaces is greater than its own weight. In these cases, gravity is still the governing force, but differences in density and fluid pressure create upward forces that balance gravitational pull. Buoyancy is not limited to water or air. It can occur in plasmas and even in astrophysical environments where radiation pressure and gas density variations play similar roles. Levitation also appears in the context of radiation pressure. Light carries momentum, and when photons strike an object, they exert a force upon it. Although this force is incredibly small under ordinary circumstances, it becomes significant in environments where gravity is extremely weak or non-existent. In space, solar sails use radiation pressure to propel spacecraft. On microscopic scales, optical tweezers, highly focused beams of light, can trap and move particles by balancing gravitational and thermal forces with radiation pressure. These interactions allow scientists to manipulate biological samples, atoms, and tiny droplets with extraordinary precision. In certain quantum contexts, levitation manifests through phenomena that stretch intuition. For instance, atoms in magnetic traps or optical lattices can be suspended in place by carefully engineered potentials. These traps confine atoms within regions of space where electromagnetic interactions create effective wells and walls, allowing atoms to hover without contact. Bose-Einstein condensates, ultra-cold quantum states of matter, can be held in place by magnetic or optical fields, essentially floating in an environment where thermal motion has nearly vanished. These forms of levitation arise from the delicate interplay of electromagnetic interactions and quantum mechanics, demonstrating that gravity can be counteracted even at the smallest scales. Another remarkable example is acoustic levitation. Sound waves, when directed and tuned precisely, can create standing waves of pressure capable of trapping and lifting small objects. The compressions and rarefactions in the air generate tiny pockets of stability where particles can remain suspended. Researchers have used acoustic levitation to manipulate droplets, crystals, and even biological samples without physical contact. Although the forces involved are small, they can be sufficient to balance gravitational pull. In materials science, levitation techniques such as electrostatic suspension allow precise studies of molten metals or heated droplets without contamination from container walls. By balancing gravitational forces with electric or magnetic forces, scientists can observe high-temperature phases or reactions that would otherwise be altered by surface interactions. This careful cancellation of forces allows contact-free experimentation, enhancing accuracy and revealing behaviors that remain hidden in conventional setups. Levitation also plays a role in planetary and astrophysical phenomena. For example, dust near stars can remain suspended by the combination of radiation pressure and magnetic forces. In some environments, magnetic fields can suspend plasma filaments above stellar surfaces. Even within galaxies, gas clouds can float above galactic disks by balancing magnetic forces, turbulent pressure, and gravitational attraction. Although these mechanisms are vastly different from those that levitate objects on Earth, they represent the same underlying principle. Gravity is constant, but other forces are often strong enough to counterbalance it. All of these examples illustrate that levitation, in its many forms, is not a violation of gravity, but a testament to the power of other interactions. Electromagnetism, pressure gradients, quantum mechanics, fluid dynamics, and radiation all serve as tools through which nature creates moments of suspension. Gravity remains ever present, woven into the backdrop of these phenomena, but it is not always the dominant force at every scale. What ties these diverse phenomena together is the recognition that gravity, despite shaping the universe on the largest scales, is globally the weakest of the fundamental interactions. This weakness is precisely what allows other forces to oppose it so easily at small scales. While gravity cannot be shielded or canceled, levitation demonstrates that nature provides many pathways to balance it. It is worth noting that levitation always arises from interactions that are local, specific, and governed by clear physical principles. There is no mysticism in these effects. The seeming magic of a hovering magnet or a floating droplet is grounded in precise, measurable laws. Yet even with full scientific understanding, levitation retains a sense of wonder. It reveals how complex and interconnected the physical world can be, how forces combine in intricate ways to create outcomes that appear to defy intuition. And perhaps there is something quietly profound in that. Levitation reminds us that even under the steady pull of gravity, a pull that shaped your bones, your world, your perception, there are moments where other forces lift things upward, creating pockets of stillness and suspension. In that sense, the universe itself shows a kind of balance, a place where nothing is entirely fixed, where forces compete and harmonize, where rising is possible even in a world ruled by falling. And as you reflect on that gentle balance, you may sense a softness in the cosmos, a reminder that even the strongest pulls can be met, and even the heaviest burdens can, for a moment, become weightless. Chapter 10. The Future of Gravity Control: What Science Allows and Forbids. For as long as humans have observed the sky, gravity has seemed both familiar and immutable. It is the force that holds our feet to the ground, binds planets to stars, and structures the cosmos. Yet as science has advanced, our conceptual picture of gravity has grown far more subtle. We no longer view it as a simple pull, but as a manifestation of space-time curvature. This deeper understanding invites the question: could future technology ever control gravity? Could humanity ever lift objects, vehicles, or even spacecraft by manipulating space-time itself, rather than relying on engines or electromagnetism? The idea carries an enormous imaginative appeal, but science draws sharp boundaries around what is allowed and what remains forbidden. To explore the future of gravity control, we must begin with what gravity actually is. In general relativity, mass and energy determine the curvature of space-time, and that curvature guides the motion of matter and light. There is no gravitational force to manipulate independently of space-time. Controlling gravity would therefore require controlling curvature. This is both a promising idea and a formidable challenge. On one hand, curvature is not something one can redirect or block in the way electromagnetic waves can be manipulated. On the other hand, in principle, any distribution of mass and energy shapes space-time. If one could deliberately engineer such distributions, one could, at least in theory, produce gravitational effects tailored to specific purposes. This reasoning leads to the most grounded and realistic form of gravity control, moving large masses to generate desired gravitational fields. This is not hypothetical. Astronomers observe gravitational interactions constantly. Binary stars influence each other's orbits. Massive planets perturb the trajectories of smaller bodies. Even spacecraft missions occasionally use gravitational assists, trajectories that steal a tiny amount of momentum from planets to accelerate through the solar system. But true gravitational engineering, in which controlled masses are arranged to produce a specific gravitational effect on demand, lies far beyond current technological capability. The amount of mass needed to generate meaningful curvature is enormous. A planet-sized object produces a gravitational pull only modestly stronger than Earth's. To produce artificial gravity comparable to Earth's pull, one must either rotate a structure to generate centrifugal acceleration, a method requiring no modification of space-time, or gather vast amounts of mass. This brings us to the idea of artificial gravity through rotation. Rotational artificial gravity is the only currently feasible way to simulate gravity in space, and it is an engineering solution rather than a manipulation of gravitational physics. A rotating spacecraft creates a sensation of weight through centrifugal acceleration, pushing occupants outward. This effect has no relation to curved spacetime. It cannot affect objects outside the rotating structure and does not alter gravity itself. It is likely to remain the primary method for generating gravity-like conditions for humans during long-term space travel. Yet the idea of controlling gravity more fundamentally continues to inspire speculation. Many of the most dramatic proposals involve exotic matter, forms of mass energy that behave differently from ordinary matter. As discussed in earlier chapters, exotic matter with negative energy density could theoretically create unusual curvature patterns. Some theoretical constructs, such as traversable wormholes or warp-like metrics, depend on such exotic energy conditions. If negative energy could be stabilized and produced in large quantities, it might allow spacetime to be shaped in extraordinary ways. But this requirement poses immense challenges. Known quantum effects that produce negative energy do so only fleetingly and in extremely small volumes. No known process can accumulate or stabilize such energy in the amounts needed for macroscopic spacetime engineering. Even if exotic matter were available, fundamental limitations in physics impose constraints on what gravity control could accomplish. For instance, gravity cannot be shielded. A device cannot simply block external curvature the way a material might block electromagnetic waves. Nor can gravity be canceled locally, because mass always contributes positively to curvature in classical contexts. A negative mass could, in theory, create opposing curvature, but the resulting structure would likely be unstable. The absence of observed negative mass in the universe suggests that nature prohibits such objects in practice, even if they remain mathematically conceivable. A more speculative pathway arises in theories proposing extra dimensions. If gravity propagates through higher dimensional space, while other interactions remain confined to familiar three-dimensional space, then it is conceivable that manipulating geometry in those extra dimensions could influence gravitational behavior in ours. Certain models suggest that the strength of gravity might vary if additional dimensions had adjustable shapes or sizes. But these ideas remain highly theoretical. They depend on assumptions about the fundamental structure of space-time that have not been confirmed experimentally. Even if true, controlling extra dimensions would require technologies that manipulate space-time at scales far beyond current capabilities. Quantum gravity, the long-sought unification of general relativity and quantum mechanics, also influences the conversation about gravity control. Some proposals suggest that space-time may have a granular or emergent nature, built from more fundamental quantum information. If gravity arises from patterns within this quantum substrate, then controlling gravity might involve controlling these underlying patterns. This conceptual shift could open new avenues for manipulating curvature, but quantum gravity remains an incomplete field. No experimental evidence yet supports specific mechanisms for engineering spacetime at the quantum level. Nonetheless, this line of speculation reveals how our deepening understanding of physics might eventually redefine what is possible. While direct control of gravity may be far beyond our reach, there are adjacent technologies that mimic some of its effects. Magnetic levitation, the use of pressure gradients, quantum traps, and radiation pressure can all counteract gravity indirectly. These are not forms of gravity control, but they offer practical ways of achieving suspension or lift. The The technologies that arise from these effects may one day power advanced transportation systems or precision scientific instruments. Still, none of them interact with gravity fundamentally. If one imagines the far future, centuries or millennia ahead, it remains possible that new discoveries could reshape our understanding of gravitational physics. The history of science demonstrates that ideas once thought impossible can sometimes become reality when new frameworks emerge. The very concept of curved space-time was unimaginable before Einstein. The discovery of quantum behavior transformed our view of matter and energy. It is conceivable that a future theory, more complete than our present understanding, might reveal possibilities for manipulating space-time in ways we cannot yet foresee. Such a theory would need to unify quantum mechanics and gravitation, reveal the microscopic structure of space-time, and provide experimentally accessible predictions. But even in the most optimistic projections, certain constraints seem likely to remain. Gravity is unique in its universality. It couples to all forms of mass energy without exception. It cannot be turned off, redirected, or shielded. Any attempt to control gravity must therefore operate indirectly by reconfiguring mass energy distributions. This makes gravity the most difficult of all interactions to manipulate. In contrast, electromagnetic fields can be controlled with enormous precision using small amounts of energy. This asymmetry is rooted in the weakness of gravity relative to the other interactions and in its geometric nature. Thus, the future of gravity control lies at the limits of physics. Technologies that mimic gravity for human comfort or for transport are achievable using rotation or electromagnetic interactions. Technologies that require true space-time manipulation remain deep within speculative territory, and technologies involving exotic matter or negative energy densities remain out of reach, constrained by the absence of such forms of matter in nature and by the stability requirements of space-time. Yet the quest to understand whether gravity can be controlled is valuable in its own right. It pushes physicists to explore the edges of theory, to test the foundations of general relativity, and to probe the quantum structure of the universe. Even if no device ever manipulates gravity directly, the search may lead to deeper insights about cosmology, black holes, the early universe, and the unification of forces. And perhaps there is something gently profound in this understanding. Gravity, unyielding and quiet, shapes the motion of galaxies and the arc of your own footsteps. It cannot be shielded or silenced. It is the silent structure beneath every moment of your life. As you contemplate the far future of physics, the dreams, the limits, and the unknowns, you may feel a calm awareness that some aspects of the universe are not there to be controlled but to be understood. And in that understanding, you find your place within a cosmos vast beyond measure, unfolding with steady, patient grace. Thank you for spending this time with me, friend. I hope this journey through gravity left you a little calmer, a little lighter, and maybe a little more in awe of the universe around you. If you're still awake and want to keep wandering through the cosmos, there's another video waiting for you right here. If your eyes are heavy, then I wish you the sweetest dreams among the stars. Good night.